Welcome, everybody, tonight. We really appreciate you coming out here on another one of our chilly evenings to hear from former Secretary and Nobel Prize winner Steven Chu. This is something we've been looking forward to for the entirety of the quarter. And as is our practice at the Institute of Politics, we generally leave the introduction, the fuller introduction of our guests to our incredible students. So I'm going to turn this over in just a moment to Yang Cheng, affectionately known to all of us as Y Squared. And Yang has been, a pillar of the Institute of Politics student community since our inception, always there asking the incisive question, and has just been a friend to all of us since she began. She came here to Chicago in 2009 to pursue her PhD in particle physics, and so that is what she's been doing since her arrival, but she's found plenty of time somehow to attend all of our events. So we appreciate that so much. And without further ado, Yang, why don't you come up here and introduce the Secretary?
Thank you, Darren, for the kind words. Energy. Ubiquitous, yet so precious. Vital, yet so controversial. From coal mines in West Virginia to wind farms in Arizona, from fracking and oil sands to nuclear and biofuels. What is the energy landscape in the United States today? And what does the future hold? A lot are at stake here. Jobs and economy, national security, the climate, and the future of our planet. When the president called upon this generation to stop the rise of the oceans and heal the planet, how many still remember the moment? And how many have answered the call? It is my great honor tonight to introduce to you one man who did answer the call, and this time directly from the president himself. Born in St. Louis, Missouri, Dr. Steven Chu obtained his bachelor's degrees from University of Rochester and his PhD in physics from UC Berkeley. He won the Nobel Prize in Physics in 1997 for his and his colleagues' work at biolabs, cooling and trapping atoms with laser light. Dr. Chu went on to pioneering work in biophysics at Stanford, and later leading the effort in biofuels and solar energy research at Lawrence Berkeley National Lab, where he was appointed as director in 2004. On January 21st, 2009, Dr. Chu was sworn in as Secretary of Energy, becoming the first Nobel laureate and first career scientist to hold a cabinet position. Or, as my hometown newspaper back in China reported, Chinese-American handed key to United States nuclear arsenal. During his tenure as Energy Secretary, Dr. Chu led the Obama administration's renewable energy efforts and helped devise the solution to the Deepwater Horizon oil spill in the Gulf of Mexico, which, by some accounts, he came up with on the back of a napkin during a banquet. Since leaving office, Dr. Chu has returned to Stanford and continues his work in energy innovation and combating global climate change, which he will talk to us about tonight. So now, without further ado, let's give a warm round of applause to our distinguished guest, Dr. Steven Chu.
So, thank you for that very kind introduction. There was not a single back-of-the-envelope calculation. There were many. And then I assembled a team of about half a dozen other people that we worked on for pretty intensively for a couple of months, 2 or 3 months, and also backed up by a lot of calculations and detailed things in the national lab. So it was a team effort. All right, so let me talk about energy innovation, the future of global climate change. So it may come of some news to you that this is the temperature from 1800 to 2011. A reanalysis of all the data and deeper data set made by a Berkeley group that actually went in thinking that the estimate of the temperature increase was overestimated, and they were going to prove that it was overestimated. And the research was funded by the Koch brothers, but with the agreement that whatever happened, happened, and it would be published. And so that's what happened. The conclusion was the previous climate people got it right, that there wasn't a bias in the temperature. Now, if you look at this, you will begin to notice that the climate has not changed. This is the average land temperature in the Earth. At least in DC, it hasn't changed in the last 10 years, therefore there's no change, okay? Which is what happened. It plateaued in the last 10, 12 years. So that's what we work with. Now, if you look at it, you also realize that over the last 30, 35 years, that's been the biggest change in the temperature. And it's not the same. This is land temperature around the world. Most of the land is in the northern hemisphere, but it's very asymmetric in the sense that the temperature is mostly in the northern latitudes, and this is the temperature difference over nearly a decade from 2009, 2009, and a little bit down here. And so because of that, there's anecdotal evidence that suggests it might have changed. This is anecdotal evidence of Muir Glacier, Alaska, taken in August of 1941 and August of 2004. It's different. This is anecdotal evidence of heat waves. This is a heat wave that killed estimated 52,000 people in August of 2003. Killed. There was another heat wave in Russia a couple years later, killed 15,000. The Chicago heat wave killed about 800. Okay? Put this in perspective. But that's anecdotal evidence. So what I'm going to now talk about is what I call climate epidemiology. I'm not going to talk about climate models. I'm not going to talk about what they predict. I'm just going to say, look, the temperature's increased, and are weather patterns changing? Just a simple question. And so, but I'm not going to take data taken by environmentalists or people like that, or NOAA or NASA. I'm going to take data assembled by reinsurance companies. And why? Because to them, it's a green eye shades calculation. Reinsurance company insure insurance companies. And insurance companies have to get insurance in case there's a catastrophic storm or earthquake or something, because they can't pay the premiums. So they take out insurance. Lloyd's of London's reinsurance company, Munich Re, Swiss Re, etc. So this is from Munich Re's data set. The number of what they call natural disasters. A natural disaster is a big thunderstorm, a series of thunderstorms, not a single storm, a big hurricane, a flood, a serious drought, forest fires that incur losses. So that's very important to realize. These are not average events. These are not within the norm. Unless there's an exceptional difference, you tend to think, bigger, stronger winds, more damage a hurricane. But there's another thing we've begun to notice. If it's not a big, strong wind, but it gets stalled somewhere for an extended period of time and dumps water, that also incurs damage. So it's not a simple metric of, category X. And so, again, actually, monetary losses is a good normalizer of all this stuff. Okay? You can't be looking at these things. So then you try to factor out GDP and all these other things. But let's just take about just number of events, and they didn't factor out GDP, the growth, wealth of the world, and they're focused mostly in the United States. So in green here, you see storms, you see floods, you see all sorts of stuff, forest fires, droughts, things. Big drought causes a lot of crop failures. And the brown at the bottom are earthquakes. And what you see is there's a rising trend, very noisy, but a rising trend. Okay, this is a partial year, so, but overall rising trend. These are insurance losses. The light green are uninsured and insured losses. The dark blue are insured losses. But I also want to point out that these are underestimates of the real losses, because these are what insurance companies call losses. Let me give you an example. In Hurricane Sandy in the New York metropolitan area, New Jersey, northern New Jersey, a lot of businesses, small businesses went out of business. They either didn't have insurance or their doors were shuttered because they had to reconstruct or something. And if you're a small business and you have to close, a restaurant, a hardware store, something, and you have to close for 2 months, there's a probability you go into bankruptcy. And I've heard estimates as high as 30% bankruptcy, but let's not, it could be as low as 10%. That's not an insurance loss. Bankruptcy is not an insurance loss. The property damage is insurance loss. Another insurance loss that's not considered a loss, New York is going to spend, on scale, $10 billion to weatherize their subway system in lower Manhattan, to weatherize the electrical system underground, because there was a long blackout in the lower part of Manhattan. That's not an insurance loss. New Orleans, federal dollars are going to help weatherize and build up the flood protection even more after Katrina, about $10 billion. That's not an insurance loss, et cetera, okay? So that's not counted in this $200 billion a year rise. That's where it's hitting in U.S. And so it's increasing and it's curving upward, and the flood insurance in the United States is backstopped by the federal government. Now, what does that mean? If I'm an insurance company and there's a major hurricane and I will go bankrupt if I paid out all the premiums, and you do your best as an insurance company to minimize those payouts, but in the end, if you can't, the federal government comes in and says, we'll give you the money. Okay, that's a backstop. And then the sentence is, well, but then, the premium should be adjusted to pay for this. And after Katrina, they could not be adjusted. And then Congress got a little bit worried, so they passed a bill that was going to go into effect in 2013. They passed that, I think, the end of 2011, beginning 2012, that said the federal government can't backstop forever, so you have to raise your rates to break even. Okay? But the rates might go up too fast, so we'll limit it to 25% per year increase, which means after 3.5 years, you've doubled it. Now, so a couple things happened. Flood lines got redrawn in the last decade. And there was I read this and I said, this is not going to work, because immediately there will be a howl from the people who bought and built beachfront property or riverfront property, and they're just going to complain about it. And when it got enacted in 2013, that's exactly what happened. No, this is not allowed. I want to rebuild my beachfront house. So it goes into the national debt. When it goes into the national debt, it stays in the national debt until we get rid of the national debt, which is not anytime soon. The national debt on flood insurance is now $26 billion and rising. And right now the cost of money is low, but when the cost of money goes up to what it used to be, that's real money. Okay? That's not an insurance loss. This is real money, and it's going to grow. And we are paying for it, but we're not pricing it into the cost of energy. Another thing in Munich Re, costliest natural catastrophes since 1950 around the world. The earthquake tsunami in Japan, the earthquake Northridge in Los Angeles, the earthquake in Christchurch in New Zealand, and the rest are weather related. And look at the dates. Since 1950, 2005, 2011, 2012, 2008, 2011, 12, Northridge was 1994, the rest were in the 2000s. Something weird is going on. Okay? So that just summarizes what I just said. In the last 63 years, 7 of the costliest losses were due to weather, and 6 out of the 7 occurred in the last 8 years. It's epidemiology. I can't say the climate models predicted this, because they candidly didn't. They're trying to get better, but they're not quite yet. So let me talk about another epidemiology. This is cigarette smoking And in the US, in 1900, the amount of cigarette smoking of American males was virtually zero, and it climbed per capita cigarettes consumed from well less than 100 per person per year to 4,500 per person per year. It was amazing. There's a big uptake during World War II because standard issue with the K rations were cigarettes. So that's this little slopes, okay? By 1950, 1960, the medical community began to suspect, where's 1950, 1960? Here's 1960. The medical community began to suspect that this must be correlated with the rise of male lung cancer deaths. It was going up too, but 20 years later. And then in 1965, 64, the Surgeon General put a first report that said, we have reason to believe that cigarette smoking is hazardous to your health. There was great resistance. The waters were muddied from 50 to the 70s by an industry that felt threatened that their market might go down, and they muddied those waters. And then no advertising television, no advertising magazines, a big public campaign to try to encourage people, if not to start, because tobacco is one of the most addictive drugs, but at least not to start. And then 20 years later, American lung cancer men deaths came to decline. Females followed later because female smoking started later. Okay? Two things about this. During the 60s and 50s, 60s, 70s, 80s, industry said, we don't understand the molecular biology. We don't have proof that cigarette smoking actually causes cancer at a biological level. We don't understand this, so there may not be true. Okay? To this day, we don't understand the full molecular biology of how these carcinogens actually cause cancers and heart disease and high blood pressure and kidney disease and et cetera, okay? But it adds to the confusion, and so as the market share declined, they had to encourage China and India and Eastern Europe and other countries to take up smoking, which they did in spades. So they moved on, but they're trying to make a comeback in electronic cigarettes, and they're the guys that it's going to help people break the addiction. But when you poll the number of junior high school people and high school people who use e-cigarettes, over half of them smoke normal cigarettes. But they're trying to make a comeback with that and candy-flavored cigars, which are less regulated than cigarettes and cigarettes. Okay, but it was epidemiology that finally got the U.S. government to take action. Okay, now this epidemiology will also occur, but there's a difference. There's a time scale of 20 years before you see the effects. What's the time scale of a greenhouse gas layer in the world? So consider energy coming from the sun hitting the earth. We actually, over the last 35 years, have good satellite data. There's an 11-year solar cycle, but it goes, we measure not only visible light, but the infrared light and the microwave radiation and the sunspot activity, the ions, and everything. And it has an 11-year cycle, and the baseline's flat over 35 years. During that 35-year period, the temperature went up. Now, the physics of the greenhouse gas is okay because energy coming in the earth, constant, energy going out, less. What happens over a 10, 20, even a 30-year period, we don't know, we can't predict. It's very complicated because of land, air, ocean interactions. Clouds are another thing, but that's on a shorter time scale. The ocean stuff is on a 10 to 20-year time scale. But we know there's a time delay. Why is there a time delay? It was mentioned I was spending a lot of time in putting out a leak of oil in the Gulf of Mexico. I was in Houston. It's in the summer, it's a very hot, sweaty place. So you stay inside. Where the oil was leaking out in the Macondo well, 1 mile deep, it was 2 degrees above freezing. The surface temperature was 86. It stays 2 degrees above freezing year-round. The temperature mixing for the surface to 1 mile deep, 2 miles deep is very long. I just gave a talk in the physics department. I said it's hundreds of years to millennia, and there was a climate oceanographer said, no, we think it's about 4,000 years. It will take for the bottom of the ocean to warm up. Okay, so meanwhile, energy in, same, energy out less, but you're warming up a cold ocean, and so when you glide to the new equilibrium, it will take at least a millennia. So the delay is a millennia, at least a couple hundred years, minimum. No one says less than a couple hundred years. Okay, that's a problem. You're smoking, and your grandchildren and your great-grandchildren will get lung cancer. And, you know, that's okay, because you won't die of lung cancer. Or is it? So this is an issue. I think the climate science is not really forthcoming in this threat of time delay. But it's a very real time, and it's not complicated. And over half a century, it doesn't become complicated. It's conservation of energy. Now, so you would not, as individuals, smoke knowing you're going to confer lung cancer or heart disease or kidney failure on your grandchildren. Yet, as a society, we're just ready to do that. So what's happening? I just pose that as a question. Now, what I just showed you was weird things happening with 1/4 of a Celsius degree over land averaged around the world. And significant weird things happening. And so I can't tell you what will happen when we go up 2 degrees more. But I think my intuition tells me that more weird stuff will happen. But if you wait 30 years to really be sure of the weird stuff, when there's a 500-year delay, it gets to be kind of too late. All right? This is a very aggressive carbon mitigation, which we will not follow. We're going to cruise past that. And so here's the present time. This was an IPCC of, I think, 2005 data and modeling. And this is what the temperature might do if we continue on a path of increased energy efficiency, but the developing world continues, and the developed world doesn't really turn its stuff down as much. And so this is what happens. But you notice it's 2100, year 2100. The climate models were loath to model to 2200 or 2300 because they said, well, Steve, we're not really sure what's going to happen at 2200, 2300. I said, yeah, so just be honest and have huge uncertainties. You don't have to be sure of anything. And in fact, the uncertainties are actually a little bit bigger than this, quite candidly, for these carbon emission scenarios, because we are just beginning to scratch the surface of what all the biological feedbacks are. So it's a question of uncertainties and risk mitigation rather than being sure. So rather than narrowing the error bars, I'd rather make them realistic and wider and just understand what the risks are. The economists are willing to apply discount rates of how much today's present value would be 300 years from now. So why can't the climate guys go 200 years out? I don't know, but that's the difference between economists and climate scientists. But, you know, this is something that Yogi Berra did not say, but he should have. If we don't change direction, we'll end up where we're heading. Now, if so we do what we're doing, I am worried about going 3 degrees and 4 degrees, but we will go much further than that, okay? So let's look at evidence of what the world was like when we were in a warmer spell. So this is the proxy for temperature. This is present time. This is going back 600,000 years. What are these green, black, and blue? These are the greenhouse gases, and you know, something weird happened. There was just an uptick in that over the last 100 years. That's just immeasurable on the scale of geological timescales. So we're in new territory over the last 3 million years. So we don't really know what's going to happen, but just recognize that the level of carbon dioxide is greenhouse gases is over 40% higher than it was over the last 3 billion years. Okay? There was a warm period. That's an ice age, stable climate. There's a warm period. That warm period, there was a rough estimate of 2 degrees centigrade higher. And by looking at sea level of life, fossil evidence of life at sea coasts around the world, the sea level was 6.6 meters higher, with at least 6.6 meters higher, with 95% confidence level, but we didn't have weather stations and weather satellites, so we don't know the weird stuff, which is actually much more devastating. We don't know the changing weather patterns and what was agriculturally, agricultural land and not. So that stuff we can't tell, but we can tell sea levels and things like that. So here's something where I want to quote someone I admire. Our ability to find and extract fossil fuels continues to improve, and economically recoverable reservoirs around the world are likely to keep pace with the rising demand for decades. I'm not talking about coal, I'm talking about oil and natural gas. I said that. The reason I say that is because the demand, over the last couple of decades has more than doubled, but the ratio of reservoirs is kept constant. And then there's even better technologies. The ability to recover oil used to be 5%, then 10%, then 20%, then 50% of the oil in the ground is now extractable. And in some places, we're going to 70%. So when you go to 5 to 50% in 30 years, you've just increased your ability to recover oil tenfold. And your ability to find oil has increased tremendously. Your ability to extract oil 1 mile deep, 2 miles deep is there. Your ability to extract oil in the Arctic is there. This is U.S. crude production. This is the peak of oil in the United States. The reason it peaked in the United States and declined is that oil was plentiful, so you can go to a different country and it'd be cheaper lifting costs rather than to try to squeegee more oil out of the United States. This was misinterpreted to mean, well, in the world we'll have a peak oil, and lots of people said it was going to happen 2000 or 2010. No, it's not. Because of the technology to recover oil is getting better and better, and if the price goes up a little bit, then you're willing to look a little harder. So at $100 a barrel, you're willing to do a lot of things. Okay, notice this little green thing, tight oil. So this is 2011, 2012. 2013, we increased the oil production in the United States by about 1.3 million barrels a day in the U.S. By the end of 2013, now 2014, our production now beginning 2014 is 8.5 million barrels a day. Another million barrels a day. It'll probably go up another million. So we're now the second biggest oil and natural gas liquids produced in the world, probably Saudi Arabia. We may catch up with Saudi Arabia and pass it. We may not, but it'll be only a short couple of decades. And if you include ethanol, we're higher. Okay, so that's oil. This is hydraulic fracturing and horizontal drilling. Natural gas, this is a company that prides itself on making good forecasts. During the last 30 years, this group, the firm, has earned a reputation for accurate forecasts of major changes in oil and natural gas prices. And so this is the actual thing on the left-hand side, and the forecast is right. This is production of natural gas in the United States. And what happened? Well, that's what happened. Okay. So, and around the world, the amount of tight oil, shale oils, euphemistically called, and gas, shale gas, is all over the world. And there's an order the crude estimate is there's an order of magnitude more the rest of the world than there is in the United States, factor 10. Okay? There's enough oil and gas on the earth to cook us. We're not going to run out in this century, certainly in this half of the century. Okay, so these are numbers, but I'll just ignore that. The reserves are 50% higher. Okay, just think 50% higher, but as the technology, that's with today's technology, but it's racing ahead, so it keeps up. So another well-known quote is, "The Stone Age came to an end not for the lack of stones, and the Oil Age will come to an end, but not for the lack of oil," said by Sheikh Yamani, the former Saudi oil minister. And the joke I did in the physics department this afternoon was, it's not, I don't think it's what made him the former oil minister. But let's just say that's what he said, but there's an implied solution. You went to Bronze Age and things like that because you transitioned to better solutions. So can we transition to better solutions? So let me talk a little bit about energy efficiency and clean energy sources. I'm a big believer in energy efficiency, so I'll give you some good news, the good, I'll give you some not so good news, the bad, and I'll give you some ugly news. The good news is appliance standards, if properly applied, actually drive down the cost of an appliance. And the blue, this is called an experience curve. So every time you double shipments, the price goes down by a certain factor. So that's common in economic development. When you get better doing something, the price just automatically goes down because you just get better doing it. And the open circles are the cost of buying a refrigerator of a similar model, and the closed circles are after a series of efficiency standards, first in California, 3 efficiency standards, and finally federal standards during this period of time. In 1973 or 74, I think California said by 75 or 76, I don't remember the exact dates, we're going to start refrigeration standards in California, but because California is such a big market, it actually turned the rest of the country. And so what happened is the price of ownership, which is the purchase price plus the price of energy, went down. How much did it go down? Well, if it was following this trend line from 1975 to today, what would have cost for the lifetime of the refrigerator, about 17, 20 years, it would have cost about $5,000, but now it's costing $3,500, $1,500 savings for the consumer. But always the going-in assumption was that a standard meant a higher efficiency standard means the price of the refrigerator went up. And there you see very clearly that the price of the refrigerator before standards and the price of the refrigerator after standards made the price go up. Not. Okay? This is some data we were gathering. Some colleagues of mine at University of California, Berkeley, were on the Secretary of Energy, and they're all physicists. So we're data-driven, So that's interesting. That was over a 60-year period. We looked at room air conditioners, price of ownership. Air conditioners is a really big deal. The purchase price is a small fraction of the use, because the electricity of air conditioners is a big deal. Price of ownership goes way down. Oops, what happened? The purchase price went down. Just data. The same with clothes washers, and the same with central air conditioners. So floor appliances in the United States, we didn't cherry pick them. We just wanted to look at the appliances that had the longest track record. We looked at the same appliances in Europe. They don't have bottom standards. They have gradations of efficiency, but the same characteristic. Okay? They constantly overestimated the cost of the standards, and what happened is the engineers very quickly just figured out how to achieve that standard at same manufacturing costs. Okay, but the standard would kick in a year or two ahead to give them fair warning. That's good news. Economists say you're limiting choice, so this is bad news, but it's good news. Price on batteries. Batteries have been going well. They're still very expensive for electric vehicles. So this is Department of Energy's what we call EV everywhere, electric vehicles everywhere. They get to be everywhere not by big subsidies. They get to be everywhere if the cost of owning a car that's a 5-passenger car with comparable performance of a $20,000 internal combustion car, and if you pay $25,000 and can go 300 plus miles, then you're starting, at today's gasoline prices, you pay for itself in 3 or 4 years. So that was the target. Can you get the cost down? It was dominated by the battery costs. So in 2008, the cost of batteries, manufacturing costs, were $1,000 per kilowatt hour. By 2012, the manufacturing costs were $500 a kilowatt hour. And so we set our audacious goals that can we get the cost of manufacturing batteries for automobiles down to $160 a kilowatt hour, 3 times less. Don't know, but if you get to that price, you got a $100 billion market worldwide, and you get the $25,000 car without subsidy. Now, once you have that, why would you want to have an electric vehicle or plug-in hybrid? Let's say electric vehicle. Because the joy of having my cell phone app and say, I'm going to come in the car in 2 minutes, cool it down for me in hot, sweaty summers, or warm it up for me in cold winters, and then it calls you back 2 minutes later and says, I got it ready, are you coming? Instead of, honey, I'm waiting for you, when are you showing up? No. So, and once you have a preconditioned car, you're not going to go back, okay? And you might be willing to stand for a 30-minute, 100-mile hit of electricity for that. Maybe not, I don't know. But anyway, so but the batteries have to improve. The founder of a battery company, Professor Yi Shui, an electric engineer, a star in battery technology and nanotechnology, wanted me to be on the board of his company, and 5 other companies did. And so I said, well, look, I don't know, but we started talking science together, and one thing led to another. And so we started developing a number of ideas. It's all very exciting. And we have a shot at developing a battery, and I'll just get to the bottom line, I'm not going to read this, which may give a density that could be as much as a factor 10 higher, maybe a factor 3 higher, we don't know. The battery density and cost, the energy density has gone up about 30%. In your cell phone, in your laptop, and your everything else, okay? And the progress in batteries over the last 10 years has been more than I've seen over the last previous 20 years or 30 years. It's remarkable. A lot of smart people are beginning to get into this because there's a huge market and because it's such an important technical problem. And then one thing led to another, and a month and a half ago, we submitted a paper to Nature on the first demonstration of some of these ideas might work. It's very exciting. And it was my first rejection from Nature for my battery research. I've been rejected in science. That science paper was rejected on our appliance standards. 3 reviews. One reviewer said, this is astounding, this is really important, it should get out. The other 2 reviewers, if I paraphrase gently, would say, this is, I'm not sure, no matter what this paper says, the economists are not going to believe it. So there you have it. And so, you know, and this one is more standard rejection. This is a clever piece of work. It's very original, but since it's not commercially viable today, maybe you should go to a specialized journal. So fine. That's a very standard Nature or Science rejection. But, so it's good. I get to reject in many fields. A little bit on energy consumption in data centers. This is 30, 40 gigawatts a year just to run data centers. McKinsey estimates that only 6 to 12% of the electricity is used to actually do something like, you know, a server like Google to send information out, or iCloud or something like that, or to crunch numbers. And the rest of it is to keep all the stuff on standby, ready to serve, and then to cool it. And so this is something. The standard is you put electricity into the electronics, most of which is wasted because it's on standby, and then you spend another 50% electricity to cool the electronics. And 5 years ago, 10 years ago, people weren't concerned about this, but it's getting to be a big deal. And so these data centers are actually using about 300 or 400 megawatts per 24/7. Okay? And I'm talking about the Googles and the Yahoos. I'm not talking about NSA. They're bigger. And Google has found it's industrially very competitive to make the amount of electricity cooling and to make their servers as efficient as possible. And so they only have a 6% surcharge on cooling their servers because they don't want to sacrifice speed. When you Google and it says 0.14, 0.25 seconds, they want to, okay. So another thing that's going to be eating into energy is mobile technology. As you go from 3G to 4G to 5G, if you take the current learning curve in electronics technology today, by 2020, we could easily be spending 12% of our electricity on communications, the nation's electricity. And if you really do it where you expect the internet traffic to grow a little bit faster, it can be 25%. This gets to be significant. For those of you who are not in California, California spends about 22% of its electricity to move water. Okay? So this is something, and so you need to pay attention to that. Before I took my oath of poverty and joined the government, I was on the board of NVIDIA. It's a company that makes graphic chips. And I was very proud of what we did while I was on the board. We started to make not graphic chips for computer games only, but we started to make graphic chips to actually do numerical calculations. These are graphical processing units, and they're called GPGPUs, general purpose graphical processing units. For those computer nerds in the audience, you may know that the graphical processing units are now the fastest way of computing around. For a few $1,000s, you can get a 2 teraflop machine. And then I said also, you want to make the efficiency really good. So it's a high-level language that the top 10 supercomputers in the world, 5 of them use this generation of chips from NVIDIA. But in addition to that, I also said, the name of the game is how many computations you can make per unit energy, not how fast you can go. It's number of flops or floating point operations per second per watt, or number of computations per unit of energy. And so this is the CEO and founder of NVIDIA, Jensen Huang, who's saying, look, the old Xboxes, and the one-year-old Xboxes and PlayStation 3s, this is the computational horsepower, and this is the Tegra K1. It's 1.5 times better, or twice as good. And instead of using 100 watts, it uses 5. So that's good, because that means, well, unfortunately it means that on your iPad and your iPhone, you can have a really intense computer game experience. But it also means for computation, it becomes much less energy intensive. Here's the ugly. When I was Secretary of Energy, I wanted to drive efficiency in the set-top boxes in case you have cable TV, Comcast, Fios, AT&T, or satellite TV. If you put your hand in those little boxes, they're warm. And so I said, well, we should really regulate this because there's no need for them to be warm. They leave them on all the time. When you think you've turned it off, you've only turned off the LED display. They leave, if you have a DVD recorder, they leave the hard disk spinning. It's amazing. And so the ones with the DVD recorders, 40, 50 watts, the others 30 or 40 watts each. Refrigerators, 18, 20 cubic foot refrigerators, 40 watts, just by comparison. That was regulated. They would have been 150 watts or 200, okay? So I said, we got to control this. And so they announced with great fanfare that the industry came to an agreement without a formal regulation, but a voluntary reduction in energy by 10 to 45% by 2017. And so my former head of public affairs, Dan Leskow, writes me an email and says, you must be very proud of this. I know it meant a lot to you. So this is a great victory. I wrote back an email, and I'll spare you some of the stuff, but I was crushed. Because I was telling the manufacturers that you can really turn it off, really dead off, and just keep a crystal oscillator clock going and a few other little sippy things. And you then wake up at 3 a.m. in the morning and download the program information. You put yourself back to sleep. And you just store it in local memory. How much memory do you need? I don't know, 50 kilobytes? Right? When it's coded, it's just stuff. And I can't price 50 kilobytes or a megabyte of memory. It's priceless, as in zero. Okay? So you can turn the whole thing off except the crystal oscillator, which, oh, by the way, a crystal oscillator doesn't take much electricity. This is a crystal oscillator. To wake itself up, look into the cable, download it for 5 minutes. People will never unplug it because it's a pain in the butt to say, we have to download the program information for 5 minutes. Okay? And then you turn it back off. That's really easy. Right? And turn off the hard disk, because that only takes a half a second to spin up. Okay? So I was saying you can do this. And then I estimated instead of 30 watts, you can get down to 1 to 3 watts. So come on, guys. And so I was doing this, and I sat down, and there's a lot of pressure from the industry, and then the industry tries to snowball the people who don't know about electronics, and they did it. And they said it's a great victory to go down by 20, 50%. And, you know, the Wi-Fi, internet, audio-visual amplifiers that take the internet and sling it around, and they go on standby. And I was looking to get off cable because, well, I'd be politically correct and just say it's not necessary. It's expensive. And then when those systems go on standby, they're 1/10 of a watt. It's a Wi-Fi internet-ready thing. Okay? It gets worse. And then, you know, I was looking at trying to get, I have very bad radio reception, and I have a classical station that's very weak. That's very classical. Classical stations don't have a lot of low power. And so, and where I live, it was horrible. And so I was thinking of using my cable because there's a couple of radio stations that I like. But then I started researching and decided I'm just going to go Wi-Fi, take the internet music, and port it wirelessly. But I started chatting with the guys who came in and charted, and they said, no, you don't, you know, if you ask us to crawl around the basement, it's going to cost $100. And I said, by the way, you know about these, you know, they're pretty warm. And so, yeah, what the cable company does is they like to recycle the electronics. The same board goes into customer after customer after customer. They put it in a new steel box, but it's the same board because, you know, hey, they don't want to spend money. And so I said, Did I look up the model number? It's on, you know, I Google around, find out how much it costs. I can't find the model number. And then internet's great. And so they say, that's a fake model number. The real number is down below. But there's a little serial number sticker with the tag, and it said, that's the real model number. They give a new box. They want to recycle the electronics because they're not paying for the electricity. Well, how much electricity are we talking about? We have 3 boxes. They give you 4. I was conservative and said, that's 100 watts 24/7. And we watch TV maybe an hour or 2 a day. But, you know, my wife and I, but we don't watch 2 TVs or 4 TVs. We watch 1. And then we turn it off. But this is on 100 watts 24/7. You multiply the number of hours in a day, days in a year, the number of kilowatt hours, 15 cents a kilowatt hour. We're talking $130 a year. Okay? That's real. $130 a year is real money. Multiplied by 90 million customers, the number of families that have cable, and I was only doing 3 boxes, not 4. It's $12 billion a year. It's the power of 10 1-gigawatt nuclear power plants a year to power these boxes, or all the coal plants in Ohio. Choose. But the companies want to recycle the old electronics to save a couple bucks. And there weren't enough technically knowledgeable people that had enough courage to say, no, we won't let them do this. So they made a deal. That's the ugly. Okay, so it helps to have a Secretary of Energy who really gets in the nitty-gritty and pays attention to this stuff and say, I'm not going to sign off on this. Okay? The politicians will not know you can go down to 1 watt. They won't, because they're not technically nerdy people. Okay, let me talk about how science and technology can change the world, energy efficient and clean energy sources. And I'm going to start with gas and oil. And this is a very unconventional view, but this is policy. And you know, we're not going to run out of it, but candidly, I don't want to paint oil and gas into a corner and make them the bad guys and shut them off, because if you do that, what you're going to do is you're going to end up having a we they, and then money talks. Okay? So you need to show a way that you can transition to lower carbon with oil and gas, so that by mid-century we're down to 1/5 of the carbon emission. Okay, so here's a few ideas. You can use natural gas and coal and electricity generation, but you better capture the carbon. Carbon costs today are really expensive, but in order to start the technology going, you want to utilize the carbon. Now, in enhanced oil recovery, you're buying the oil companies in the Permian Basin, Texas, they buy carbon $20, $30 a ton. They try to squeegee out oil to get to that 50% recovery. They try to recover as much as possible so they can use it again, but they kind of lose half of it. And then you can say, well, it leaks out. Well, maybe so, maybe not. Another technology thing, we are getting very good at very dirt cheap, inexpensive infrared diode laser technology that can tell if carbon dioxide is leaking out of a borehole or out of a fissure or something like that. We're getting really good at methane leaks to pick that up as well. So if it stays underground, which you can monitor for 100 years, it's going to be mineralized. That part we know. So, because you're trying to squeegee out the oil, but it's stuck there and it mineralizes. And if you monitor it and they lost it and it's underground, give them credit for it. The technology, but don't do an average of average wells. Measure each well. Okay? So it's, again, a cheap technology that will allow that to happen. Otherwise, other people say, well, we don't want to give them credit for something that's going to leak out, and I agree. But the thing is that cheap infrared technology is now upon us. And also methane, which means fugitive emissions, so you can catch the methane leaks and everything else. Number one. Number two, it may be possible to capture carbon at $15 to $20 a ton. Right now it's $80 a ton, and then another $20 to pipe it and compress it. And so the techniques we have today, either it's so-called amine techniques, MEA, or chilled ammonia techniques, or oxygen separation, are too costly. They will double the price of electricity if deployed today. That's unacceptable in the rest of the world, let alone the United States. Okay, but if it's $15 a ton, another $20 to pipe and compress, and it's the fossil energy is 1/3 of the energy, now you're talking less than 10% increase in the average price of electricity. So this is now tolerable. Okay, if you're 70% renewables, let's say, and you're 30% this, and then you're capturing it and compressing and storing it that much money, and then you give credit for some of the carbon loss, and then it becomes even cheaper. So this is possibly a way. I'm not pipe dreaming this. My time is very precious. I joined a startup company that thinks they can capture carbon from coal and natural gas at $15 a ton. And if we fail, it might be 20. If we really fail, we go bankrupt. But I think it's real, and it doesn't violate the second law of thermodynamics and that other stuff. And so, like I said before, monitoring CO2 and methane, 20 years ago, a little infrared chip cost $1 or $3, can tell in parts per million changes in this room. Let's say I'm talking now for 50 minutes, and you're getting sleepy because the carbon dioxide has come up, and that That was 20 years ago. Okay? And finally, we're going to have to capture carbon not only from power plants, coal and gas plants, fossil fuel plants, but we're going to have to capture carbon from steel making and cement. The coking process, the cement making is hugely carbon intensive. And so we need to do all those things. Now consider this. As you go less steel, more plastic in a car, or steel to aluminum plastic, for lighter weighting, for better mileage. And then when you want to recycle the aluminum, you want to recycle the steel, but you want to separate out the plastic. And if you can recycle plastic, fine. If you can't, put it in landfill, but make it biodegradable, because then it's sequestered forever. Okay? Biodegradable is not necessarily a good thing. Okay? Biodegradable stuff dumped in the ocean, a really bad thing. But biodegradable on land is not necessarily a bad thing. It's a sequestered form of carbon. And then there's I think at $40, $50 max, you change the formula. And so if you're building a building of steel, cement, or composite material, and there's a price of $40, $50 a ton, and then if you can, when you demolish the building, you try to recycle some of the steel, you try to recycle cement, but cement doesn't recycle well. It can no longer be, it can be filler up to an extent, it can't be structural, it can't be cement anymore. Okay? But if a composite material sequesters carbon, well, hey, let's make an adjustment for this, and so it's a different thing. So these are radical ideas, but let's start the dialogue. Okay? Make it economically better to use it, and then it goes away forever. Or recycle it. Electricity is getting better. It's the second cheapest form of new energy. New gas is cheaper, but in a decade, if price of natural gas stays between $4 and $6 an MMBTU, 1,000 BTU, wind will be cheaper. And anything above a wind 3 site. And including transmission, but you need storage. But the battery storage is getting better. Solar energy is getting better. This is the price of solar, again, a learning curve, order of magnitude, another order of magnitude reduction in cost as production goes up. There was an over-investment and oversupply. The price plunged, it went back up to about 80 cents a spot for a watt capacity of generation. But companies now are saying the target is 50 cents a watt within the next 8 years. If we can't make that, we won't survive. Okay? It used to be $5 a watt about 8 years ago. So the price of solar panels, think about that. $30,000 car now costs $3,000, the same performance. That's good. It's really good. Now, however, that's the module. The land use, the construction of the land use, the hookup, that's not. So these are called soft costs. For residential, it's the price of installation on the home. There's the licensing. The city or town says you got to get an inspection before you're allowed to put it up because your roof might fall down. And you got to get an inspection afterwards to make sure before you hook up the grid and all those other things. And then they extort a little money out of you and make it, the license application a DMV experience. And so there are industries that say, we'll stand in line for you if you pay us some money. And so if you look at a residential solar installation in Germany versus the United States, for the whole thing, so many watts of generating capacity for a certain amount of sunlight power, it's $550 in the United States, it's $250 in Germany. Oh, it must be the price of labor. Not. People spend 1/3 of the time on the roof than Americans. So the technology's there. Okay? And then don't use this licensing fee as a way to prop up city revenues. Make your money on parking meters and parking tickets and speed traps. Don't make $1,000 for solar, okay? So we, 2.5 years ago, said, hey, the technology is getting really good. We're going to start to shift our focus on decreasing what are called the soft costs. Okay, the installation, the licensing, all these other things. And the current program manager of Sunshot, Min Lee, says, unlike physics, where you can fundamentally figure out the upper limit for the efficiency of solar cells, there's no such limit for bureaucracy. Okay, so, and so we're putting our dollars where they're going to do the most good. We still invest in technology development, but I think this is very proud of starting ARPA-E. This is the Advanced Research Projects Agency for Energy, modeled after DARPA. It was proposed by the report called Rising Above the Gathering Storm, chaired by Norm Augustine. I was on that committee. And then I was sent to Congress by the committee to try to convince Congress to support it. And I was also sent to the Department of Energy when I was at Berkeley Lab to try to convince the Department of Energy to support this and to start a new funding agency within the department that would be swinging from the heels. Instead of doing incremental improvements, you expect 9 out of 10 to fail, but you want game-changing home runs. You don't want infield singles, and you don't want to violate the second law of thermodynamics, so you need really smart people to decide what was snake oil and what was not. And then in the congressional hearing, where they had a bunch of people with me, and they wanted people who were against it and people for it, but in the end it was remarkable. A former DARPA person, a former Homeland Security, DARPA, which did not work at all, was held an example, don't do this. Why? Because DARPA worked because it had one customer, the military, but the Department of Energy doesn't have a customer, it's a private sector. And so, but it was after 2 hours, it was decided, if you hire the right people, it will work. No matter what the structure is, if you hire the wrong people, it won't work, no matter what the structure is. So I would send to the Department, the Secretary of Energy, a good man, Sam Bodman, was, okay, but the career folks said, no, we don't want to do this. And so, because it might crowd out basic research, and we just don't want to touch it within the Office of Science. So Secretary Bodman said, okay, I could do this. So the new Secretary of Energy had a totally different attitude. That was me. So anyway, one of the things we invested in was, we weren't actually asking for just proposals. Those people were really good, so they actually went out and decided to call for proposals. What needed development? A little infusion of money for a couple of years might transform our options, which is very different than passively saying, we'll review what you submit. Again, you need very, very good people. A whole bunch of people. I recruited a friend of mine, elected to the National Academy of Sciences in his early middle 40s, but when he came to DC, he was 46. Why would a star professor come to DC when you're elected to the National Academy of Sciences in your early 40s? Okay, because it was the opportunity, and a whole bunch of people will be elected to National Academies. We had 6 in the National Academy of Sciences and Engineering. That was a big deal. And they recruited like-minded, quality people. That really changes things. So this was a project we invested in Cree, semiconductor transistor, not of silicon, but silicon carbide. And for reasons I'm not going to go into, within 2 years, they were producing a 1 megawatt, 20,000 volt transistor the size of my pinky. Okay? That could transform the way we step up and down electricity. So I'm going to skip. That's me when I was 32, about Bell Labs. The attitude, and let me say very briefly, the attitude that I had is, I spent 9 years at Bell Laboratories early in my career, and this is a bunch of people that were hired very young, in their late 20s or 30. They weren't hiring stars, and yet 17 people who worked there went on to get Nobel Prizes. And in this thing, I learned about these very frank and animated, excited discussions where another person called it constructive confrontation. Someone would say something and say, I don't believe that. You're wrong. You're full of crap. So you go out on the board and you work it out. And that's what we started doing in ARPA-E. It's not taken personally, okay? It's just the quality of your idea. I'm not insulting you, and just work it out. And so this is pictures of 5 of us hired when we were 30 or 28 or something within a 3-year period, and 3 Nobel Prizes. So I'm going to skip that. So I talked about EV audacious goals and batteries, which I think we'll meet. We talked about Sunshot, which the module part we will definitely meet. It's the soft cost part, which I'm worried about, but we're marching down. I talked about RPE, which is really looking for home runs. And everything, and people who know me who were in my group as graduate students and postdoc, and what I was telling these people is the greatest danger for most of us lies not in setting our aim too high and falling short, but in setting our aim too low and achieving our mark, which is said by Michelangelo. So, now, people ask, knowing what I knew today, would I have become Secretary of Energy? Because I'm a scientist. I actually never campaigned for anyone in my life, as in publicly supported anyone, okay? I was a pretty hardcore scientist, and when I was asked to give advice to the candidate Obama by Harold Varmus, he said, oh, by the way, are you a Republican or a Democrat? So I said, well, I'm mostly a Democrat, but I've been giving advice to the previous administration, so if they call me up, it's okay. I'm going to do that too. I said, that's fine. So anyway, what I didn't like, so the greatest thing I liked about Washington is I was able to bring in some really good people, get on the phone and call people and say, look, come join me. Down to not assistant secretary or undersecretary or something like that. I mean, program manager and sub-program manager. So when the secretary of energy calls you up and they respect you and say, come to Washington for just a couple of years. It actually matters. And what I like best about that is when you get really good people, like the people in RPE or the people in Sunshot, and you then start to block and tackle for them. Don't let the rest of the bureaucracy drag them down. Just stay out of their way. Arun Majumdar, he was told, you can't go and talk to people in Congress. We, the political interface, are the ones, or the secretary goes, but you can't go. And I told him, no, I'm sorry, the congressional liaison people in the Department of Energy. Sorry, he gets to go. And as you probably know, he was a great charmer of Congress. Okay? So that's blocking and tackling. Now, what I didn't like is the press. They sit there hoping you'll make a mistake, trying to get you to make a mistake, and then spinning something so even if you don't make a mistake, it looks like a mistake. And there's a couple of really outrageous ones, and then how do you react to that? Finally, it got so bad. It was during a congressional hearing, and Politico ran this incredible story. The Secretary of Energy doesn't care about American submarine hot gas prices, and I was constantly accused for the first 3.5 years of doing everything I could to increase the gasoline prices in the United States. Now, I have to confess, every morning at 8:30, I would do those dials. And until the price started stabilizing, then they stopped, And they said, well, when you took office, the price of gasoline was this, and look, I said, when we took office, we're, in free fall recession. But never mind that. It was so outrageous that we sent them the congressional transcript, and Politico published a retraction. But it didn't matter, because the damage was done. The next 3 months, I was crucified in the blog sphere by the conservatives, even though they published a retraction. This is the way it works. So press, it's tough. So it was agreed that I would announce that I was stepping down on February 1. I told the president at the mid-end of November that I couldn't do this anymore. My wife was anxious to go back to California. And so, and she said, you got to let it go. I said, maybe I'll stay another year or two of this stuff I wouldn't do. She said, no, you got to let it go. Everything's replaceable, including you. And I'm going back to California. Oh, coming. Okay. So on February 7th, 6 days after I made the announcement, The Onion publishes the story with this picture. Hungover energy secretary wakes up next to solar panel. I'll read you part of the story. Washington. Sources have reported following a long night of carousing at a series of D.C. watering holes. Energy Secretary Steven Chu awoke Thursday morning to find himself sleeping next to a giant solar panel he had met the previous evening, going on to allege that I didn't even remember the manufacturer's name. According to sources, Chu's encounter with the crystalline silicon solar receptor was his most regrettable dalliance since 2009, when an extended fling with a 90-foot wind turbine nearly ended his marriage. Now, my wife was very understanding. That's what they all say. But she looked at that photo and said, "You don't have hairy arms." So I was safe. Okay, so I walk in the morning, February 7th, and my publisher says, "We got to answer this." So, okay, we can have a little fun answering this. So this is part of the answer. Quote, "I just want everyone to know that my decision not to serve as second term as Energy Secretary has absolutely nothing to do with the allegations made in this week's edition of The Onion. While I'm not going to confirm or deny the charges specifically, I will say that clean, renewable solar power is a growing source of U.S. jobs and is becoming more and more affordable, so it's no surprise that lots of Americans are falling in love with solar." And I said, "Regardless of your sexual orientation," but they, no. Okay, so, now, here's another thing that I've been trying to communicate to utility companies, and I'm going to stop because you're looking nervous. The cost of modules has plummeted. The goal in rooftop installations will be $2 a watt, and that's pretty cheap. I'm not sure about Chicago, but in California, where I live, that means for $10,000, you can generate a lot of electricity. The cost of batteries is plummeting, so in maybe 5, maybe 10 years at the outside, a $10,000 or $12,000 system will allow me to go on average 80% off grid. Okay? So that's pretty exciting because of the battery costs and everything. And so this is a technology that could be as disruptive to electricity generation distribution as the internet. So here's the problem. So I was telling utility companies, this is coming down the line, so let's think of a new business model where you can profit from this. Okay, so here's the business model. Utility companies get to borrow money as inexpensively as just about anyone in the United States. They're in a flat to shrinking business, and as solar and batteries especially get cheaper and cheaper, they're going to see their customer base of the best customers do this. So they may get FedExed, as the post office got FedExed. They took away the best customers first, the ones who pay the bills, because they have the capital. They will have $10,000 or $15,000. So I said, how about a different business model? Do the business model where you partner with a light nimble company that figures out how to install cheaply, because I don't expect a utility company to figure out how to do that. But you borrow money, so you own this stuff. And this is not a radical model. This is called the telephone system model, where the telephones own the phone. They rented your phone for so long, they maintained it. So the utility company partnership with a private company owns the modules. They own the battery. They use your roof. They sell you electricity for cheaper than what you would have paid. What's in it for you? You get 10 kilowatt hours of storage in a little thing this big. And if there's a blackout, what do you need? You need 40 watts for your refrigerator. You need a couple, 23 watts is a compact fluorescent bulb, so you need 500 watt hours a night, 300 watt hours, okay. By then, the set-top boxes will be fixed. So you don't need the 100 watts for that. You get blackout resistance for at least a week. So you can keep your refrigerator and your freezer going. You have lights at night. You can't run your air conditioner, but you can run a fan. Okay? This is good. What is the utility going to get out of it? They get to put a battery in a protected environment. Out of the rain, out of the cold, a little corner garage. They get to put solar in the batteries where they want the most, the end of the distribution system for grid stability. And they get to put solar on a roof that distributes, so no transmission lines, no environmental impact statements, stuff like that. Okay? So that's what's in it for them and for putting it on buildings. So this is good. I started talking about this 2 years ago to regulators and utility companies. I have a few roundtable discussions, invited them in. They're in 3 classes. Class number 1, tell us what to do. So I said, this is what you should do. You got to work with the regulators. There may be some monopoly companies. You can work through that. Another class, deer in headlights. And the third class is we're going to fight this. We're going to make higher hookup charges. Okay? In fact, there was a settlement of announcement of, and it was, if you go back and read it, it's all about hookup charges. Now, they think they got it solved, but wait a minute. At 1%, 2%, is an issue. Then it gets to 20%. Are you going to increase the hookup charge? The Hawaiian Electric Company, retail cost of electricity, 37.5 cents a kilowatt hour, because they generate electricity from diesel and bunker oil fuel. That's why it costs so much. They get a lot of sun in Hawaii. If you don't live in Hilo, but in most of the rest of Hawaii, you get, on average, 265 sunny days per year. Price plummeted, they started investing in solar. At 2% solar, the Hawaiian Electric Company said, we're not going to allow anyone else to hook up solar to the grid because of grid stability. That's another bullshit argument. That's like the box stop sets can only go down by 10 or 20%. 20% electricity solar is a grid stability issue. 2% is not. 5% is not. Okay? But instead of saying we can own the solar and the batteries, we're gonna fight it that way. But then if you have a hookup charge of $5 today, 5 years from now it's going to have to go higher, and 10 years from now it's going to go higher, and it's a band-aid. So you need a better business model. So it's been talking about that for 2 years. After this year, I'm going to stop. I hope some of you talk about it. Okay? Let me return to this image of Earthrise. Apollo mission, the first one orbited the moon. Last orbit, they turned the capsule to Earth and took this picture. And the astronaut, Bill Anderson, who took the picture, said, we came all this way to explore the moon. And most important thing is we discovered the Earth. Since Christmas Eve 1968, we've discovered that the destiny of Earth is changing due to humans, and we've got to do something about it. So I call upon this image because this is a bleak lunar landscape, not a good place to live. This looks pretty good from here. Nowhere else to go. Okay? So we better take care of it. And think of the smoking analogy. We're smoking to give heart disease and lung cancer and everything else to our grandkids. That's not responsible. So, we have a moral responsibility to the most innocent victims of what we're doing. Because the world's poorest people, they can't adapt. They don't have the resources, and the ones yet to be born. So that's all I have to say. Thank you.
I realize that some of you may have to leave. Do you have a few moments to take just a couple of questions from the audience? We'll do why don't we take 3 or 4 questions here, and then we'll break and continue on for the evening. Let me go all the way to the back with that hand near the rear, and we'll get a microphone to you. Yes, ma'am.
Hi, Dr. Chu. My question's about methane and the methane leakage from all of these frac wells, and also the methane hydrate at the bottom of the oceans that might be triggered by the warming of the seas. Can you talk a little bit about all this methane release?
Sure. the verdict's not in actually how much methane is leaking out from hydraulic fracturing. There's certainly evidence that some of it's leaking out for sure, but the verdict's not in how much. But the issue is whether you can ensure that much less of it leaks out than otherwise. It's not going to be a lower temporary bridge to a renewable energy. And so I go back to what I said before about infrared spectroscopy. I'm doing this in my scientific work now on biological systems, and the ability to remotely censor or even to have local sensors of methane is really very good. And so if you overfrack, you should be able to, they're beginning to capture methane leaks from old natural gas infrastructure pipes. There's methane leakage there. There's, if you don't properly seal the well, you drill, you put a seal casing, you properly cement, or if you don't put casing in and you have methane leakage up there, you can see it, and then you can stop it. So it's a matter of proper monitoring, proper regulation, proper enforcement in order to stop what's happening, but also proper measurement to see what's really happening. Methane hydrates in the ocean, high pressure, cold temperature, takes hundreds of years. So it's not imminent that methane hydrates in continental shelves are going to come up. Paleontological evidence long ago suggested there might have been explosive releases long ago, 50 million years ago, thermal spikes. There's more methane seepage in the northern tundra where you don't have microbial action in the peats, and so we're seeing more of that. So it's happening. It's one of the positive feedbacks of warming globe, especially in the northern latitudes, because these peat bogs that are frozen, it's like meat in a refrigerator. It lasts, I keep it at 34 degrees, really cold. It lasts a week in the meat drawer. If you put it in a freezer, it lasts a few months. My wife won't touch it after a month, but it lasts a few months. What's the difference? A few degrees. The microbes wake up. And so when the tundra wakes up to microbial action, it's a very nonlinear process. And so that's one of the concerns that people have.
Let's get a hand up over here, and then we'll come up front for our last question.
Good evening, Secretary Chu. My name is Edward Wang. I'm a second-year PhD here at the Booth School. You probably don't remember me, but we did shake hands after you officially announced the opening of the Greater Philadelphia Innovation Cluster in 2010. I still vividly remember that picture in my head. So thank you for being here with us tonight and sharing us with your perspective on environmental preservation. My question today for you is that given that China and the U.S. are the two biggest energy consumers of the world today, how can public and private sectors work together? How can institutions and individuals work together to really reduce energy consumption and really make sure that we leave a world that is just as sustainable to our next generations as it is today?
Well, we're not in a sustainable world today. But it's a good question. So while Secretary of Energy, we started a cooperative agreement between China and the United States. It's a small amount of money. It's $300 million. But it was in three areas. It was in building efficiency, not as demonstration buildings, but cost-effective buildings that would pay for themselves after they're constructed in just lower energy costs. Because that's what's going to move the needle. Not a demonstration building. It costs a lot of money. But it's about money. Energy is about money. Energy-efficient buildings, electric vehicles, carbon capture and sequestration. Each country put in half, but then the companies had to put in half. And it was the first time the United States and China had a mutual research agreement where we would, if we co-invented, we would share the intellectual property patents, and we would could develop, each of us could develop in each other's country. So it was more a start of cooperation than anything big, because $300 million is really nothing. So, but you know, it's a start. China is highly likely to put a price on carbon. They're starting to do this already within the next 5 years. I think between 5 years, 8 years at the outset, this government in China will put a formal price on carbon.
One last question.
Secretary Chu, thank you for coming this evening. Here at UChicago, like at several colleges, we have a pretty substantial divestment campaign trying to get the college to divest from different fossil fuels. I was wondering if you could maybe share your thoughts on that technique. Do you think it's viable?
No. I'm trying to not paint oil and gas into a bad guy corner. If you do, you set up the battleground. And I'm trying to give them ideas in order to say, like I said in that slide, okay. I'm not sure you can do it with coal, but quite candidly with coal, the coal industry, I still believe that we have to do carbon capture and sequestration for all the other sources of carbon, no matter what, and the technology has to be cheap enough that China and India will do it, okay? So, and that's research, and research is cheap. I don't want to be spending millions, hundreds of millions, and billions of dollars on demonstration where we know that technology will not be viable for deployment. That is not a good thing. Now, if the divestiture and things like that, you should divest from tobacco companies and things like that. But right now, if there's a chance to bring them on board, let's do it. Most of the major oil companies now have a ghost price of $40 and $50 a ton on carbon. Why? Because they're making investments 20, 30 years into the future. Shell, ExxonMobil, Chevron. They're saying now, in the last 6 months, climate change is reality. And they're carrying that on their books and how they make their investments of billions of dollars. So let's give them ideas on how to do that. That's why I was thinking these are radical approaches for ideas, and a modest price of $40, $50 will be enough, I think, if you have a long dozen-year horizon, because engineers, once you get it away from the lobbyists and you get it to the engineers and scientists, magical things happen. That's what happened to refrigerator appliance standards. That's what happens in everything. In SOx, NOx, that's what happened in seat belts and catalytic converters and mufflers and everything. They were original price for catalytic converters for smog was $2,000. Go back and look. Aftermarket, if you poisoned your muffler, it's $200 retail. OEM, I don't know what it costs, probably $100, $50. This is what happened with technology. It was SOx control, NOx control in power plants was totally overestimated by an order of magnitude. After 4 or 5 years, 10 years max, this will happen. But get it away from the lobbyists and get it to the engineers and say, we are marching along this path, and that's what China's going to do. We are marching along this path. We have to do this. Okay? So they're carrying a ghost price on carbon now.
Want to take one more? Take one more? All right, we'll go right here. One final question.
Secretary Dr. Chu, thank you for coming tonight. I'm Craig Sieben, Sieben Energy Associates here in Chicago. Knowing what you know today, if you were to go back to starting at DOE, right at that point when we could have put a price on carbon in the U.S. Congress, and the decision was 85% cooked, what argument, what shift might you have done today differently to potentially influence a different outcome?
Yeah, great question. Great question. The House bill got way too complicated. They let all the special interests get there and make an 800-page bill to make little advantages for a little here and there, and that just was wrong. and that there wasn't enough White House leadership on the Senate side. Okay, but the Senate wasn't going to do it because they had maybe 54 votes. Okay, and because there are a couple of Dems that wouldn't do it either. Here's what I would do today. You have to keep it simple. Cap and trade philosophically does work, but you have to keep it brutally simple. But right now, it has such a bad name. Even though cap and trade worked in Bush 1 for SOX and NOx, it just has a bad name now. And it has in the trading schemes in Europe, because they gave out too many, you know, whatever they call them, coupons or whatever, the credits, that it drove the price too low. You need a steady price increase to go to $40 a ton so industry can know what will happen. You have to give them certainty in what to invest in. So the best way to do that is just tax it. But what do you do with the money? Give it back to the American people. How? Well, a lot of people are retired, they're unemployed people. Mail them a check each month. We know that, you know, and it's a progressive way of giving back the money because, you know, your electricity bill goes up a little, your gasoline bill goes up a little, but here's the money you can spend on whatever you want. The big bad government's not going to tell you what to do. So if you want to buy a 50-mile-per-gallon car, that's okay. Here's the money. You decide. No government program. Revenue neutral. Okay? Really simple. All of a sudden, industry, it's mostly I'm looking at the private sector investments, industry will say, I get to know what's happening with certainty in the next 12 years, and then you would cap it at $50 a ton because that's going to be good enough, at least for a decade, another decade, and we'll see what happens. That, knowing if I were not Secretary of Energy, that's not good enough, nor is President of the United States, Emperor of Energy, now we're talking. That's what I would do. Really simple. You know, George Shultz and I talk a lot, and he has exactly the same attitude. I don't know if, I didn't talk to him about how do you give it back, but a very simple tax, slowly rising, give industry time, give them certainty.
Some of you don't know that Dr. Chu has spent most of the entire day engaging with students, with faculty and others here on campus, and obviously the talk tonight caps a day long of activities. At the Institute of Politics, we seek to bring people here to expand and contextualize the conversation, to sort of inform and engage us and ultimately inspire us to engaging ourselves with the political process more deeply. I can't imagine a more fitting speaker tonight. Please join me in thanking Dr. Chu for his inspiring, sobering, and insightful remarks. Thank you very, very much. We appreciate it.